Hello everyone. In today's session, we will understand singular value decomposition, also called as SVD. The equation for singular value decomposition is A equals U sigma V transpose. What it necessarily means is you can decompose or factorize any type of a matrix. It can be a square or a rectangle matrix, it could be a singular matrix, non-symmetric matrix, any matrix for that matter. You can factorize it into the form of U and V, which are orthogonal matrices, and sigma, a diagonal matrix. It is similar to your equation for diagonalization. Let me write that down. S lambda S inverse. Or for symmetric matrix, we have already seen the S matrix is nothing but your orthogonal matrix. So the equation changes to Q lambda Q transpose, where Q is your matrix of eigenvectors, lambda is your diagonal matrix of eigenvalues. So this SVD equation is very similar to that. We will now understand how we have come to this equation. We all know the concept of row space, column space. We have seen the concept of transformation using matrices. We will use those concepts. So let's start with row space, column space. So your row space is in the field of Rn and your column space is in the field of Rm. We are aware of the row space and column space diagram. Right? So imagine a vector v1 in your row space. Let this be your v1. You will multiply it with matrix A, or you will get a transformed vector u1, which is nothing but u1 is equal to, sorry about that, u1 is equal to a v1. What does this mean? You are transforming a vector v1 or mapping a vector v1 to u1 vector, which is m dimensional while your input was n dimensional, using the matrix A. Basically your matrix A is doing the job of rotating the vector and stretching the vector. Okay, now imagine we have two vectors v1 and v2 which are orthogonal in row space. So you have v2, which also you will transform to get u2, that is given by a v2. Right, now we already know v1 and v2 are orthogonal. Let's assume a little ahead that it's orthonormal now. What is orthonormal? The magnitudes are 1. So if your v1 and v2 are orthonormal, will your u1 and u2 also be orthonormal? They need not be, right? So we will try to separate out the rotation part and the stretching part of your equations. Now just rotating means the magnitude doesn't change. So let's assume u1 and u2 are orthonormal, and doing a v1 you actually end up with sigma 1 and sigma 2. Okay, let me rewrite the equation. So what you get is AB equals sigma u. Here u is your rotational part of the output, sigma is your magnitude part of the output, which corresponds to the stretching. Now if you write this in the matrix form, you will end up with AB equals, you have u1 up till um, and you have a square matrix with sigma 1 sigma 2 in your diagonal. So sigma forms your diagonal matrix, u forms your orthogonal matrix. Now finding v, u both simultaneously is a difficult task. So what we actually do is take the product A transpose or A transpose A. Let's start with A transpose A and understand what exactly happens. A transpose A. So U sigma V transpose the whole transpose into U sigma V transpose. Now this becomes V sigma transpose U transpose U sigma V transpose. Since U is your orthogonal matrix, U transpose U becomes identity. In short, we can eliminate that. So we are left with V sigma transpose sigma and V transpose. The middle term sigma transpose and sigma will yield a matrix, again a diagonal matrix with squared terms in the diagonal. So you end up with sigma 1 square, sigma 2 square, it goes on. So A transpose A is a symmetric matrix. It will yield you lambda values which are sigma 1 square, sigma 2 square, and you have orthogonal matrix V. Similarly, we can observe for A transpose. For A transpose, let's substitute the equations. U sigma V transpose into U sigma V transpose the whole transpose. So you will end up with U sigma V transpose into V sigma transpose U transpose. So again, since your V is an orthogonal matrix, V transpose V reduces to identity. Sigma and sigma transpose will give you a diagonal matrix of square sigma terms. So A into A transpose or A transpose into A, both are symmetric matrices. You can use the equation Q lambda Q transpose, similar analogy. To get your sigma 1 squares, you have to find eigenvalues of A transpose or A transpose A. Find the eigenvectors which will form U or V respectively. Now let's take an example. Let's start with a simple 2 cross 2 matrix to understand how SVD works. Okay. Consider A is equal to 3, 0. Let me just clear the whole thing. Okay. Now let's start. A equals 3, 0, 4, 5. So what is your A transpose? Your A transpose becomes 3, 4, 0, 5. So let's compute A transpose A. If you multiply A transpose A, it will be 3, 4 into 3, 4. That's 25. Then 3, 4, 0, 5. That's 20. 20. The last is 4, 0, 5 into 4, 5. That's 25. Now let's compute A transpose also. If you compute A transpose, you will end up with the matrix 9, 12, 12. So how much does this come to? 41. Okay. Let's start with A transpose A. We can observe here first, both A transpose A and A transpose have given us symmetric matrices. So let's start finding eigenvalues for A transpose A. For A transpose A. For A transpose A, eigenvalues would yield determinant of 25 minus lambda, 20, 20, 25 minus lambda should be equal to 0. So if you write this in the equation form, that's the quadratic equation, you get lambda square minus 50 lambda plus, how much do you get? 25 into 25 minus 400. So 625 minus 400 gives you 225, which is equal to 0. If you solve this, you get lambda 1 as 5, lambda 2 as 45. Now what we have to understand is this lambda 1 is nothing but your sigma 1 square. This is your sigma 2 square. Okay, whether you are finding eigenvalues for A transpose A or for A transpose, the lambda values have to remain same. So we will look at that part. So for A transpose, let us solve the eigenvalues, that is 9 minus lambda, 12, 12, 41 minus lambda should give you 0. So the quadratic equation comes to lambda square minus 41 is 50 lambda plus 225. So again, what is your lambda 1? It's 5. That is nothing but your sigma 1 square. Lambda 2 is 45. That's your sigma 2 square. So we have observed lambda or the sigma 1 square, sigma 2 square values remain same irrespective of which matrix you choose. Now we have to find V and U. So let's start finding V. For finding V, which matrix you will choose? A transpose A. So for A transpose A, we have already got sigma 1 square, sigma 2 square, which is lambda. We have to find V. How you will find V? Choose lambda equals 5. So the matrix reduces to 25 minus 5 is 20, 20, 20, 25 minus 5 again gives you 20 into x equals 0. So if you apply row operation, this row becomes 0. So what will be your x? Your x will be your free variable set to 1. Minus 20 by 20 is minus 1. And we have to orthonormalize it. So that becomes 1 by root 2. So this is your V1. Let's look for the second lambda. That's lambda equals 45. What will be your matrix? Your matrix will be 25 minus 45 is minus 20, 20, 20 and minus 20. So again, if you apply the row operation, your second row becomes 0. Correct? Again, your x is 1 and 1. If you orthonormalize it, 1 by root 2, 1, 1, which is V2. Now there are two methods of finding U. Let's use the matrix, the lambdas, to find the vectors U. The other method is using the equation. We will solve both the methods and we'll see we get the same answer. So let's use the matrix, that is A transpose. So if, oh sorry about that. So let's start with lambda equals 5. What will be your matrix? 9 minus 5 is 4, 12, 12 and 41 minus 5 gives you 36. What will be the row operation? R2 equals R2 minus 3R1. So that will yield you a 0, 0. So your x is variable set to 1. Minus 12 by 4 gives you minus 3. Right? Right. So what's the normalization here? You get 9 plus 1 root 10. This is your U1. What is your eigenvector for when lambda is 45, the matrix would end up as minus 36. Okay, this matrix is too small. Minus 36, 12, 12 and minus 4 into x is 0. When you apply row operation again, you get this as a 0 and a 0. So if you try to find your null space, you end up with 1 by 3, which is nothing but multiply the whole thing by 3. 1 and 3, 1 by root 10. You can call this as your u2. This is one method of finding u1 and u2. The other method, let me just show you. We already know the formula. AV is sigma u. So individual vectors we will take. So your ui is AVI by sigma I. Okay, and similarly, if you want to find VI, you can find VI using this formula. Okay, so using these two formula, if you have one vector, you can find the other vector. So let's use this formula now to find UI. So if you want to find U1, the original matrix was 3 0 4 5 into, what is your V1? Let's go back and check out. Oh, we went a little too back. Yeah, your V1 was minus 1 1. So it was minus 1. There is no decimal point. Minus 1 and 1 divided by root 5 into root 2. So what is this give you? 1 by root 10. If you multiply, you end up with minus 3 and 1. Similarly, u2 is 3 0 4 5 into your v2 vector is 1 1 divided by root 45 is 3 root 5 and the normalization factor is root 2. So you end up with 1 by 3 root 10, 3 and 9. So if you cancel out this 3, you get 1 and 3. So you have found u1 and u2 using vectors v1 and v2. So just verify if you will get this matrix. Okay, so what is your u? 1 by root 10 minus 3 1 1 3. Your diagonal matrix is root 5 0 0 root 45, that is 3 root 5. Then you have 1 by root 2 minus 1 1 1 1. Verify this. I hope this example was clear. Shall we take one more simple example of a rectangular matrix, then conclude this session? Let me just clear this canvas. So yes, let's take one last rectangular matrix example. to show that any matrix can be decomposed or factorized using SVD. So let's take this matrix of 1 1 0 1 minus 1 1. So you end up with A transpose of 1 0 minus 1. This is a 0. 1 1 1. Let's quickly compute A transpose A. And A transpose A, you get a 2 cross 2 matrix 0 3. What about A transpose? We end up with a 3 cross 3 matrix. You get a 2 1 0 1 1 1 0 1 and 2. We can observe finding V is easier. Why? We have already have a diagonal matrix, so we will find V, then we will find U. Okay. Oh, sorry about that. So for A transpose A, we are finding the lambda values, that is sigma 1 square, sigma 2 square. So what is the lambda here? 2 minus lambda 0 0 3 minus lambda should be 0. Your lambda 1 is 2, lambda 2 is 3. Now we will move on quickly to find vectors v1 and v2. Okay, when your lambda is 3, you get a matrix minus 1 0 0 0 into x should give you 0. So what's your x? 1 and 0. This is nothing but your v1. Now what happens when your lambda is 2? When your lambda is 2, you get 0 0 0 3 minus 2 is 1 into x equals 0. That will give you a eigenvector x as 1, because that's your free variable, and a 0 here. This is your vector v2. We can observe v1 and v2 both are orthonormal. Now let's find u1, u2 and u3. Why u3? Because it's 3 cross 3. U matrix is a 3 cross 3 matrix. So let's start finding u1, that is A v1 by sigma 1. A v1 is given by your original matrix 0 1 minus 1 1. What is your v1 matrix? 0 1. What is your sigma? 1 by root 3. Remember, lambda 1 is 3 is equal to sigma 1 square. So sigma 1 is root 3. So you end up with 1 by root 3 1 1 1. This is your u1. What about u2? 1 by root 2. Your matrix A v2, which is 1 0. You end up with 1 0 minus 1. And we have to find u3, but we don't have v3. But we do know they are orthogonal to each other. So assume your u3 is vector a b c, u1 transpose u3 should be 0. This is your equation for proving two vectors are perpendicular, right? Similarly, u2 transpose u3 is 0. So if you do this, you end up with 1 1 1, this is 1 by root 3 into a b c, it's 0, which actually gives you the equation a plus b plus c is 0. This is 0. Similarly, the other equation, root 2, you get 1 0 minus 1 into a b c should give you 0 as a minus c equals 0. You can solve it as a simultaneous equation where a is equal to c, you substitute it back, or you could solve it as a null space equation where you construct a matrix. I will choose the latter one. Should give you 0. So if you apply row operations on this, let me change it directly over here. So what is the row operation you will apply? R2 equals R2 minus R1. So this becomes a 0, this becomes a minus 1, and that becomes a minus 2. So which is your free variable? Free variable is C. If you substitute C as 1, you get B as minus 2. You get A value as 1. And you have to normalize this. What will be the magnitude? It is root 6. So this is your U3. So we have observed any matrix A can be factorized, right? Now I will rewrite the general equation once again and end today's session. Your equation A V equals U sigma. If you have a matrix of M cross N, your V will be M cross N, U will be M cross M, your sigma will be M cross N. So this, or if you take this to this side, it becomes V transpose. Okay, that's your equation of SVD. Thank you.